Hello students, in today's session I am going to discuss some important conversions related to haloalkanes and arenes. Particularly first video I will discuss about the conversions involving haloalkanes. So haloalkanes are those compounds where either chlorine or bromine or iodine or fluorine is attached to a hydrocarbon chain. So here I have taken bromoalkane. That with this example I am going to teach you various conversions. Okay, so first thing what I am taking is I am reacting this particular haloalkane with alcoholic KOH. So alcoholic KOH is nothing but KOH dissolved in ethanol. Okay, KOH dissolved in ethanol is alcoholic KOH. This prefers what is called as beta elimination. Beta elimination, already you might have studied it. So I will just give you a small hint. Supposing that you have CH3 CH2Br. Now what happens is bromine from here and one hydrogen from this carbon gets eliminated, and it leaves as HBr, and thereby it gives you an alkene. So if you want to convert a haloalkane to an alkene, you can use alcoholic KOH as the eliminating agent. Okay, so it prefers beta elimination. What is the reason why this is called as beta elimination is that, see, this carbon is bearing the functional group bromine, so this is called as the alpha carbon. Next to this carbon is your beta carbon. So since beta hydrogen is getting eliminated here, it is known as beta elimination. So if you want to convert haloalkane to an alkene, you can use alcoholic KOH. Supposing that if I use aqueous KOH, I am not going to witness elimination here, rather it is going to be a nucleophilic substitution. Hydroxide ion goes and attacks this bromine and it gets substituted as hydroxide. So if you want to convert a given haloalkane to an alcohol, you can use aqueous KOH. But if you want to convert this haloalkane to an alkene directly, you can use alcoholic KOH. Okay. Now what happens is, if I suppose add HBr to this, so addition takes place via Markovnikov's addition or Markovnikov's rule, where negative part of the incoming group, so bromine is a negative part, it binds to the carbon bearing least number of hydrogen across the double bond. So here you can see that there is one hydrogen and here there are two hydrogens. So as per Markovnikov's addition, bromine gets added here. So this is actually, you can expect the bromine here. So this is actually an isomer of this compound. So isomerization also can be carried out by this scheme. Okay, this is the first scheme. So instead of alcoholic KOH, if I use aqueous KOH, then nucleophilic substitution will take place. Here your bromine alone gets substituted by the hydroxide group. So this results in the formation of an alcohol. So haloalkane to an alcohol, if you want to convert, you can use aqueous KOH. Okay. The next scheme, a continuation of that I have given here. If you use any concentrated acid like sulfuric acid, what happens is this OH and one hydrogen from this carbon, it eliminates as water, minus H2O, it eliminates as water and it again gives you an alkene. So this reaction is also called as dehydration of alcohol. Okay. So if you want to dehydrate the alcohol, what reagent you should use? You should use any concentrated acid. Okay. So next part of this conversions in haloalkanes will be reacting the given haloalkane with magnesium metal in any dry solvent, preferably ether. Okay. Ether, you might have already read about ethers. Ethers are organic compounds which have bridged oxygen. So there will be two alkyl groups on either side and oxygen will be forming a single bonded bridge between the alkyl groups. Okay. So why we are using ether in this particular reaction is magnesium is a metal. Okay. And this compound, when a haloalkane reacts with magnesium, what you get is a alkyl magnesium halide. Okay, you can see the alkyl magnesium halide, and the polarity of this alkyl magnesium halide is also very important to understand these reactions. Okay, so the alkyl part always will have a negative polarity and magnesium will always have a positive polarity. So by reacting with magnesium, the haloalkane, we are planning to generate a nucleophile. So this part is becoming a nucleophile. Okay, so this nucleophile can undergo a nucleophilic addition across any carbonyl compounds like this. For example, if you have carbonyl compound C double bond O like this, then this alkyl part, that is CH2 CH2R. This alkyl part is having negative polarity and it can attack the carbon. So thereby it can cause nucleophilic addition across the double bond. The reason why we are carrying out this reaction, that is Grignard reagent, in moist free conditions, that is in the absence of water. This is a very famous board question in CBSE exam. Many a times this question has been asked directly, like why Grignard reagents should be prepared in moist free conditions. The reason is this Grignard reagent becomes unstable in the presence of moisture. Okay, what happens is, supposing that if there are traces of moisture, then you will get the corresponding haloalkane, this R CH2 CH2, one more hydrogen gets added to this carbon and you get a corresponding alkane. This magnesium bromide, you will be getting Mg, OH and Br. So in the presence of trace of moisture also, the Grignard reagent becomes very unstable and it will give you an alkane. This is an alkane. So remember, Grignard reagent should always be prepared in moist free conditions. That is why we are using dry solvents like ether. Okay, and the nature of this Grignard reagent is also very important. We are generating a nucleophile, that is an alkyl nucleophile. Okay, so alkyl part becomes a nucleophile and it can add across the cardinal compounds. So whenever this kind of Grignard reagent adds across an aldehyde, you are going to end up with a secondary alcohol. So you can convert given haloalkane to a secondary alcohol by reacting it with first you have to react it with Grignard reagent, then you have to react it with a aldehyde. Okay, this is a very important scheme. Then sometimes you can also react it with carbon dioxide. So carbon dioxide's carbon also acts as a excellent electrophilic center, because two oxygens are attached to carbon, they are highly electronegative in nature. So what happens is they will suck all the electron density from this carbon. So naturally what happens, your Grignard reagent can also react with carbon dioxide and it will give you a carboxylic acid. So if you want to convert a given haloalkane to a carboxylic acid, then you can use this scheme. First you have to react it with Grignard reagent, then you have to react it with carbon dioxide. Okay, what if the Grignard reagent is reacting with a ketone? Here I am taking acetone as the reacting molecule as a substrate. So if the Grignard reagent is reacting with acetone or a ketone, you end up with a tertiary alcohol. So using Grignard reagent, you can prepare primary, secondary and tertiary alcohols. For preparation of primary alcohol, I have already given you can use aqueous KOH. Apart from that, using Grignard reagent, you can also prepare carboxylic acids. Okay, so this scheme is also very important in exam perspective. Then supposing that if it is given, if it is asked to convert a given haloalkane to amines, it's very simple. You take ammonia gas and react it with given haloalkane. Ammonia being a neutral nucleophile, you will get a amine. Okay, so this is also simple. Now next one, I hope you would have spotted out easily. It is a named reaction where I will just give you the clue. Let me not spoon feed you. I will not give you the entire name of this reaction, named reaction, but you can always spot it out. See, there are two molecules of haloalkane which is reacting with the sodium in the presence of dry ether. Okay, so and you can see that there are twice the number of carbons in this reaction. So this part, 2 carbons are there. Here you can see those 2 carbons. Apart from that, this carbon, that red color part of the alkyl group also gets added, and you can see 4 carbons. So what is the name of this reaction? You can put it in the comment section, the name of this particular reaction. Okay, the last one you can see that we can also convert a given haloalkane to ether. Okay, you can see the ether, there is a ethereal oxygen present here. So this can be accomplished very easily by Williamson ether synthesis. In Williamson ether synthesis, we take sodium alkoxide. This is your sodium alkoxide, which will be a nucleophile. It goes and substitutes the bromine, and you will be getting Williamson's ether synthesis as ether as the major product.